Okay, the second kind of error bound that we're going to learn about is for when the series is not alternating. It's a little bit trickier at first, and the theory behind it is pretty complicated and it looks scary, but I do promise that in practice it's not hard to use this idea to get the correct answers to the question you're being asked. So be patient. When we see some questions, especially the AP questions, you'll see that it's pretty predictable what you have to do, and usually you can kind of guess right, get the right answer. So let's first look at kind of what we're dealing with here. For any non-alternating series, a Taylor series about x equals a, the remainder after a partial sum of nth degree terms, of nth degree, we'll call that s sub n, is bounded by, so that's just the language behind it, the error bound. We're trying to find a limit to what the biggest remainder could be. And it's a little bit ugly, so just be warned. That remainder has to be less than this m that we'll talk about in a second, over n plus 1 factorial times the absolute value of x minus a to the n plus 1. What I want to make sure you notice right away is this plus 1 here. If we're talking about the nth remainder, the remainder after the nth degree term, then the number we're going to put in the factorial, the number we're going to put in the exponent, and in a second you'll see the number we put in the derivative, we'll see what that means in just a second, are all one more than that. That is the most important thing to remember. So this m is the maximum value of the n plus 1th derivative of f anywhere on the interval between a and x. The reason why we talk like this is because we usually don't know the exact derivative at all levels, at every point on the Taylor series, at every point on a function, especially when we're expressing that function with the Taylor series. But usually what we can do is find the maximum possible value within that range, and we use that number here. That doesn't make a whole lot of sense yet. I get that. Let's see how it works in practice, and then hopefully it'll make a little bit more sense. So what we're going to do is estimate e squared using the 11th partial sum. And remember, the 11th partial sum of e is really a 10th degree polynomial. That's why I'm calling it S10. And then we'll figure out the error. So first, let's kind of use the 11th partial sum to make that estimate. The function, e to the x, we hopefully remember this already, is the sum of x to the nth over n factorial. So if we're going to use the 11th partial sum, that means f of 2 is approximately equal to the sum from n equals 0 to 10. Because again, the 11th partial sum means 11 terms, but that's going to be the 10th degree of 2 to the nth over n factorial. And I certainly could make that list and add it up, but it doesn't seem to be a very good use of my time. So what I'm going to do instead is just use Desmos to get that sum here. The sum from n equals 0 to 10 of 2 to the nth over n factorial. And that is 7.38899. So that is our best estimate for the value of e to the second. But we know it's not right, because we only used 11 sums out of a list of an infinite number of sums, so that can't be quite right. So the question is, how far off are we? And that's what the Lagrange error bound is for. Now, the reason we're doing this is because e is an irrational number that I can't exactly raise to the second power by hand. I can't raise an irrational number to the second power, which doesn't make much sense. And so when I talk about the derivatives of e, I'm going to have to face that. We'll deal with that in just a second. So the Lagrange error bound tells us, like we saw a second ago, that the biggest that the error could possibly be is this m divided by n plus 1 factorial times x minus a to the n plus 1. So we know, we'll get to the m in just a second, but we know that we're talking about, we used a 10th degree polynomial, so we're going to have to use 11 factorial here, and x minus a. Remember, it was a Maclaurin series that we used, and we plugged in 2 for x. So 2 minus 0 is 2, 11. And so notice how when we have the 10th degree polynomial, the error has to be less than the m, which we'll get to in a second, over 11 factorial times 2 to the 11th. And then let's just talk about this m now. M is the maximum value that the 11th derivative, m is the maximum amount that the 11th derivative of x could be anywhere between 0 and 2. Now, this 11th derivative of f. Now, we know that the 11th derivative of e to the x is e to the x. The problem is, and so then the maximum that this could possibly be, so the highest that the 11th derivative of f gets is e to the second. The problem is, I can't use the number for e to the second while I'm trying to estimate what e to the second is. The whole point is I don't know what e to the second is. So we need to come up with another number to use. And so what we'll say is we know that e is something less than 3. So I know that m is something less than 3 squared. And since that is, the idea behind using a number for m is to use some number that I know is like, it's a little bit bigger, hopefully just a little bit bigger, but it's bigger than the biggest possible derivative, 11th derivative. And so as long as I have a number that is somewhat bigger than what I know the 11th derivative of f is when x is 2, I can plug it in here. So I can use that 9 over 11 factorial times 2 to the 11th as the, and say that that is the maximum amount that my error could be. And if I do the math here, Desmos, and we will say that my error, so I'm going to call this r, it's really the error bound, is 9 divided by 11 factorial times 2 to the 11th. Now, I'm not doing this by hand, but this is all math, arithmetic we can do. So my error is something less than 0.00046,176. And so what we're saying is that my estimate of 7.38899 could be off by as much as 0.00046. Well, let's just take a quick look at this. I'm going to call this, I'm going to give this a name here, call this A for my estimate. E to the second power is really 7.389. My actual error, put this in the absolute value, the actual error between my guess for what e to the second is and what e to the second actually is 0.00006. So you can see that I was actually a lot closer than my error bound, but that's good. What that means is we have a reliable system for figuring out that we are confident that our actual error is definitely less than our error bound, and that's our goal.